Hey guys, in this video we'll be going over the solutions to Lab 1. Now hopefully you've had a chance to try these problems by yourself. I mean, the best way to learn math is to try a lot of problems and make a whole bunch of mistakes and then go back and figure out where you made the mistakes and why. With that said though, I hope that this video or this series of videos will be a helpful resource, especially if you get stuck on a particular question or you need to see somebody go through the steps of the question. So let's start with the first question here. It's asking us to explain the geometric significance of solving a system. So before we get into that, let's just talk about what a system is. So a system of equations is exactly what you think it is. It's just multiple equations that you're trying to solve for the x, y, z, whatever variables. So let's do sort of an example here. Let's go 2x plus 3y equals 7 and 5x plus 8y equals 2. So right here, these two equations are a system of equations. So really it's intuitive. You guys already know what it is, but just to make sure that we're on the same page. And we should keep in mind that these two equations here are representative of, in our case, they are linear equations. So that means that they represent lines. That's what we're dealing with in linear algebra. So essentially to solve a system means that you're looking for an x and a y value that works in both equations. So you're looking for an x value here that you can plug into both of these equations, and a y value that you can plug into both of these equations to get their respective answers. So thinking about this more geometrically, you are all familiar with x and y coordinates. So in this case, finding the x and the y value would be representative of finding a coordinate pair that both of these lines have in common. So the coordinate pair, both of these lines contain this point. Okay, so that should kind of help us out with trying to understand geometrically what's going on here. So just drawing my graphs here. So we have to figure out what it means geometrically. First of all, we'll try a unique solution. So a unique solution. So let's say we're considering these two lines that we have here. We'll go, this one is our line 1 and this one's our line 2. So we have we'll draw line 1 right here. And sorry. So we'll draw line 1 right here. So we know that if we have a unique solution, that means that we have one solution, which means that there's one point in common among these two lines. So you can visualize that as simply two lines with one intersection point right here. So this right here would be our solution. So this would be our solution to our system of linear equations right here at the intersection point. So that's all it means, is that if you have a unique solution that your lines cross at one point, they intersect once. Now, going forward with that thinking, if we have no solutions, then that means that there's no x value and no y value that you can plug into both equations and get the correct answer. So there's no point that these two lines share in common. So you can kind of imagine already that it's going to look like two lines that don't intersect, so two parallel lines. There's no intersection points, there's no solutions to the system. Okay, so two parallel lines. Next is infinitely many solutions. So to have infinitely many solutions, that means that there's infinitely many solutions to this system. In other words, there's infinitely many pairs or points of x and y that will satisfy these equations. Because of that, you can imagine, you can imagine it to be two lines that are essentially the same line. And I'll draw them a little bit skewed here. They're meant to be right on top of each other, but just so that you can kind of see what I'm talking about. But if you take a look at this, every single point on this line is, or on these lines, I guess is more correct, is an intersection point because they are the same line. So that's what it means to have infinitely many solutions. So just to recap, the geometric significance of a unique solution means that there's one intersection point between the lines, and the geometric significance of no solutions means that there's no intersection points between the lines, and infinitely many number of solutions means that it's the same line. So for question 2 now, this question is asking us to determine whether the system has a solution. So that's what it means to be consistent, is that it has at least one solution. And notice I said at least one solution, so it can have a unique solution or it can have infinitely many solutions. So that's also, we got to figure that out too. So before we start, let's just go over that, a couple of the things given in the question. So these boxes denote a non-zero number. So usually I like to imagine them as the number 1, and the stars, they can be any arbitrary number. So I typically like to visualize them as being zeros. It makes it a little bit easier when you get started with these questions. So we're going to go over the basically what it looks like to have a unique solution, what it looks like to have no solutions, and then also infinitely many solutions. So let's just do an example matrix here. We'll do 1, 0, 0, 0, 1, 0, and I don't know, let's do 5, negative 3, and 2. So something like this is going to be a unique solution. And the reason why it's a unique solution is because if you look at every single row here, there's a leading 1 in every row, okay? And if you look at every single column here, there's a leading 1. So when there is a leading 1 in every single row and there is a leading 1 in every single column, then you have what's called a unique solution. So next we'll do no solution. So let's do 5, negative 3, 2 again. So right here, there's no solution. And the reason being is that if you look at the bottom row here, you can see that you have a whole bunch of zeros equaling to a non-zero number. So if we think back to what it actually means to solve a system, what you're essentially saying is 0x plus 0y plus 0z equals 2, which you know just logically it doesn't work, right? So 0 cannot equal 2, so therefore there's no solution in this matrix. So whenever you see a row of zeros equaling to a number, you know that particular system of equations has no solution. So that's another thing you can look out for. And the last possibility is you have infinitely many solutions. So for this one, you can clearly see that you have a row of zeros here, and it's completely fine to have a row of zeros, so 0x plus 0y plus 0z equaling 0. It makes sense, right? So for these ones, you're looking at, if you look at all of the rows, you notice that, yes, the row 1 has a leading one, row 2 has a leading one, but row 3 doesn't have a leading one. So in this case, you're going to check if your row that doesn't have a leading one, if it's equal to 0. And if it is, then you have infinitely many solutions. There's also one other possibility for infinitely many that you should be on the lookout for, and I'll just do an example of it. So it will look something like this. So you see here, we're going to go through and check our rows and make sure that they have leading ones. So yes, there's a leading one in row 1, and yes, there's a leading one in row 2. And just like we did in the first example, we're going to check the columns to see, yep, there's a leading one in this column, there's a leading one in this column, but we notice there's no leading one in the last column. So this indicates that we have infinitely many solutions. So this is actually called a parameter, and we'll get into that later. But it's essentially a free variable. So yeah, this is infinitely many solutions. So you can look back to this and see what it looks like and the pattern of it for when you're trying to solve these particular equations. So we'll get into the more specifics of how you solve these questions, and it's important to know how to solve these questions because they will be on the midterm. So the first thing that you're going to do is check leading ones in rows. Okay, so if it's true, so if there are leading ones in every single row, you know that at least the system is consistent. Okay, so you know that it has at least one solution. Now, if it's false, if there are not leading ones in every row, then you know that, well, you have to check. It may not be consistent. Okay? So that just meaning that in this case, it can either be infinitely many or no solutions. In this case, it can be also be infinitely many, or it can be a unique. Okay? So number 2 is we're going to check leading ones in columns. So if there's leading ones in all of the columns and there's leading ones in all of the rows, then there's a unique solution. If there's leading ones in all of the rows, but not in all of the columns, then you know it's an infinitely many solutions. And then of course you can check, you'll check earlier on if there's something of the form, 0, 0, 0 equals 1 or something like that, then there's no solutions. Okay, so first step, check the leading ones in the rows, and second step, check the leading ones in the columns. So let's scroll back up here and do that on our system. So we're looking at the rows first. So there's a leading one in row 1, so check. There's a leading one in row 2, a leading one in row 3, and a leading one in row 4. Great. So from this we can conclude that the system is consistent, at least. So in this case it's either infinitely many solutions or it has a unique solution. Okay? Next, we're going through the columns. So check the column 1. Yes, this column has a leading 1. This column has a leading 1. This column has a leading 1. But we see right here, this column does not have a leading 1, right? So because of this, we know that our system is consistent, but it has infinitely many solutions. Okay, so if you had this on an exam, you would write something like, yes, the system is consistent. It has infinitely many solutions. Okay. So yeah, the trick with these questions is making sure that you're following the steps. 1, checking the leading ones in rows and knowing what it means if there is a leading one in every row, and knowing what it means if there isn't a leading one. And then the second step is checking the leading ones in the columns. All right, so same type of process with the next question. Our first step is to check leading ones in columns. In rows. And our second step is to check the leading ones in the columns. Okay. So checking the rows here, we have a leading one here, we have a leading one in the second row, and a leading one in the third row. So from this we can conclude already that the system is consistent. Now we just need to figure out, okay, so it's consistent, that means it has one solution, once again, at least one solution. So is it infinitely many solutions, or is it a unique solution? That's where we check the columns. So this column has a leading one. This column also has a leading one, and our last column has a leading one. So in this case, the solution is unique. All right, so just to conclude, the system is consistent and has a unique solution. Okay. So next question is similar. So we're checking rows first for leading ones, and then we're checking columns. So the first row has a leading one, second row has a leading one, third row, and fourth row. So we have a full set of leading ones. So we know that the system is consistent, right? So once again, now we're doing the columns to figure out whether it's infinitely many or a unique solution. So first column has a leading 1, second column has a leading 1, third column does not have a leading 1, fourth does, and fifth does. So we're missing a leading 1 for the third column, and that tells us that there are infinitely many solutions. So the system is consistent. And has infinitely many solutions. Okay, so next one, we're going to do the same process. So number 1, check rows, and 2, check columns. And we're checking for leading ones. So leading 1 here, leading 1 here, leading 1 here, but there is no leading 1 here. Because of that, we don't know whether the solution is, or if there is a solution. So we don't know if the system is consistent or not. So it can either have no solutions at this point or infinitely many solutions. So we're going to just think about this now. This, remember, we're calling it 1, right? This, we're thinking of it as 0. So you can already see, if you remember the kind of patterns that we did above, that it's looking something like this. So a bunch of zeros equaling a non-zero number, and we know that that's not possible. So already we know that there's no solutions. Now if we wanted to do it in kind of a different way, we could think about what our set of row operations would be on this system. So you can see that right above this one, so this guy right here is a non-zero number. So if this one, let's say this one is 5 and this one is, I don't know, this one's 1, okay? So if this one is 1, then our next row operation would be that we're going to try and make this bottom row also 0, right? So we're going to try and make this one 0, so we'd go row 4 minus 5 row 3, and that would give us 0, and our number right here would still be a non-zero number. So whatever it is, 1, 2, 3, 4, 5, it doesn't matter, because you can see that right here we have 0. So if we subtract 5 times 0 from whatever this square number is, we're still going to end up with that square number. So no matter what, we're always going to get 0, 0, 0, 0 equaling some non-zero number, and this is impossible. So we know that there are no solutions, and in other words, the system is inconsistent. This next question has 2 variables in it, and we have to choose an H and a K so that the system has no solutions, a unique solution, and infinitely many solutions. So our first step here is going to be putting it into row echelon form. Okay, so we're going to have to do row reduction. So before we do this, I'm just going to quickly remind us of the steps, or of the things that we're allowed to do with row reduction. So row reduction, we can interchange rows. Okay, so what we can do is we can switch the order of these 2 rows, and it won't affect our calculations. And we can also multiply rows by a scalar. And notice that we don't ever talk about dividing rows. We can multiply. So if we wanted to, for example, we wanted to divide this row by 2, we would actually talk about multiplying it by its reciprocal. So multiplying by 1 over 2. That's a kind of an aside, but important to note. And last thing is that we can add and subtract rows from each other. And we can add and subtract multiples of rows from each other. So let's go ahead and write this one out. So we have 1h2 and 2 4k, I think. So the first step is, for me, I'm going to look for a leading one in the top left corner, or in the position 1 1. And yes, it's there. So we're going to use this one to kill everything below it. So that's the idea with row reduction, is we're trying to clear the columns using that leading one. So everything except for that leading one should be gone. So in this case, what I'm going to do is I'm going to go row 2 minus 2 row 1. And it's going to give me something that looks like, once again, the top row doesn't change. So we're just doing an operation on the bottom. So it's going to look like 0 and 4 minus 2h and k minus 4. So we get here, and we notice that right here. Now, if we were to experiment with values for h, we would notice that if you plug in 2 for h, so if h equals 2, then you'll have 4 minus 2 times 2 equals 0. Okay, so that's something important to note. And here we want to notice that if k equals 4, then we'll have 4 minus 4 equals 0. Something also important to note. So the question is asking us to determine for what values of h and what values of k do we get a unique solution. So remember, a unique solution is when there's a leading one in every row and a leading one in every column. So in this case, we would need this whole thing here. We would need that to equal to 1, or we would need it to, in another way, we would need it to not equal 0, right? Because if it equals any other number than 1, we can always multiply by that number's reciprocal. So for example, if it equaled 5, we could multiply that whole row by 1 over 5, and we'd still get a leading one. So essentially we need it to not equal 0. So we know that it equals 0 if h equals 2, right? So as long as h doesn't equal 2, we have a unique solution, right? So let's try that out just to make sure that we're right. So let's say h equals 1, okay? So 4 minus 2 times 1 equals 4 minus 2 equals 2, right? So, and we can multiply that by 1 over 2 to get 1, right? Let's try h equals 0. So we have 4 minus 2 times 0 equals 4 minus 0 equals 4. Okay, so that works out also. If h equals 2, like we said above, we have 4 minus 2 times 2 equals 4 minus 4 equals 0. And we can never have a unique solution if this value equals 0. So yes, this is true. So h cannot equal 2. Now, since we've considered h, we know that to either have an infinitely many solutions or to have no solutions, we need a row, in this case, a row of zeros, right? So we actually need this 4 minus 2h term to be 0. So we need 4 minus 2h to equal 0. And that means that h has to equal 2, right? So now how do we differentiate between infinitely many and no solutions? Well, now we have to look at our second term here. So now we're going to consider our k value, right? So we have k minus 4. Let's say if k minus 4 equals 0, so we have two cases really. If k minus 4 equals 0, and if k minus 4 does not equal 0, right? So in other words, another way to say this is that if k equals 4, right? And another way to say this is if k does not equal 4, right? Because if k equals 4, we have 4 minus 4 equals 0. If k does not equal 4, it's going to be a non-zero. So let's say we have 5 minus 4 equals 1. So it's a non-zero. So if k equals 4, then that means that we're going to have the last row looking like this, 0. And because we've agreed that 4 minus 2h has to be 0 in this case, we'll have 0, 0, and then we'll have another 0. And this looks like infinitely many solutions, right? A row of zeros. Right? Now, if k does not equal 0, so we have 0, 0, and then let's use this example again, and let's say we have 1. Well, we know we have 0 plus 0 equaling 1, and this means that there's no solutions. Okay, so in these type of questions, you have to consider first your whatever the value is in here, so in this case your h value, and then you have to consider your k value to differentiate between infinitely many solutions or no solutions. So to conclude, we would have a unique solution, infinitely many, and no solution so it's unique when h does not equal 2. There's infinitely many solutions when h equals 2 and k equals 4. And then there's no solutions when h equals 2 and k does not equal 4. So this question is just asking us to find the general solution of the system. So we're just doing row reduction here, and we kind of went over that in the last example, what we're allowed to do with row reduction. If you don't remember, then you can just scroll back in the video. So we have a system here. And remember, we want to bring our system to row echelon form or reduced row echelon form. So we want it to eventually end up looking something like this if possible. And this doesn't have to be zeros. So we want it to end up looking something like that. So we want to get these diagonal ones happening. And the way that we're going to do this is we're going to look for, you're always going to check if the top left corner has a leading one in it. And if it does, then that's great because you can use it to kill all of the other things that are in that column. So you're trying to clear the columns so that the leading one in that row is the only thing that's in that column. Okay, so in this case, how would we get rid of this one right here? Well, a row operation that we could do is we could go row 2 minus row 1. And so we'll see that this one is just, the resulting one is actually 1 minus 1, so is 0. The next one is going to be 0 minus 1, and that equals -1. Next one is going to be 4 minus 0, and that equals 4. And then the next one is 2 minus 1, and that's 1. Okay, so now we can see we're almost sort of like this one, but the one thing that's missing is that we need to, this one is a leading one. It's negative, but you can easily multiply the whole row by a negative sign to change it to a positive, so it will just look like this, the leading one. But we're going to use it in its negative form right now to kill this one, because once again we want it to be the only leading one in that column. So our next step is we're going to do row 1 plus row 2. Okay, so row 1 is going to be, this one's going to be 1 plus 0, so we're going to end up with 1. Next one is going to be 1 plus -1, so 1 minus 1, 0. And the last one is going to be 0 plus 4. So we're going to have 4 here. And the second row doesn't change at all. So we have -1 here, and we have 4 here. And then we have 1 plus 1. So we have 2 and 1. Okay, so for this one now, all we have to do is multiply row 2 by -1, and then we'll get the closest to what we were looking for. So we have 1, 0, 4, and 0, 1, -4, 2, and -1. Okay? So this is what we have ended up with. And we notice that, as we talked about before, there's a leading one in this row, there's a leading one in this row, and there's also a leading one in this column and a leading one in this column, so these guys here, right? But we notice that this row, or sorry, this column right here, it has no leading one in it. Okay, so as we've talked about before, it would indicate infinitely many solutions. So now we kind of get into what this means algebraically. So there's no room for another 1 here because there's not enough rows. You can see that. So when this happens, we have, as I talked about before, what's called a parameter. So this one right here is going to be called a parameter or a free variable. So we essentially have remember what these stand for, x, y, and z here. So in this case, our z is going to be our free variable. And what we're going to do for that is, let's actually write out what we're saying here, so it makes it a little easier. We're saying 1x plus 0y plus 4z equals 2. And we're saying 0x plus 1y minus 4z equals -1. Okay, so what we're saying is that right here we can choose this to be any value here. Okay, so we can choose z to be any value, and these equations will be true. So right now we're going to call it a different letter. We're going to call it z. We're going to call it to be t. Okay? So we're going to call it t, and if you remember from high school, you had this sort of notation here. Is the element of z, you must have seen, is the element of the reals. So this just means that t is any integer. Okay, so integer being the whole number, so 1, 2, 3, 4, 5, 6, 7. So we're choosing t to be any integer here. Okay, so we can see that if we move everything over to the other side here, right? If we're moving it over to the side because we want to solve for x and y, what we're going to end up getting, so we're going to solve for x first. Let's solve for x, and we're going to get x, because there's 0y, we don't have to concern ourselves with it, but we're going to see that x equals -4t plus 2, because remember t is z now, okay? So we're going to get x equals -4t plus 2. Now let's do the same thing for y. Let's solve for y. Okay, so y equals 4t minus 1. Okay, and we don't have to solve for z because we've already solved for z in a way that we've called it to be t. Okay, so the general form, or the general solution, is going to look like this. So you're going to want to write your x, y, and z kind of in a 3x1 matrix, and you're going to write beside it essentially exactly what we have here. Okay, so you're going to write x equals, you can say 2 minus 4t. Okay, y equals 4t minus 1, and z equals t. So this right here is the general form of the solution. So this is our solved system, and yeah, that's the general solution. So the general solution is always, if it has infinitely many solutions, you're going to choose whichever variable, whichever column doesn't have a leading one. You will choose that to equal to some integer, so you're calling it t, or you can call it s or k or whatever you want to call it, and then you're going to write your other variables in terms of that free variable. So this problem is similar to the previous problem, our last problem that we did, and the only difference is that we can see that we're given equations here instead of matrix form. So we have to put the equations into matrix form here. We talked about this before, that the rows, they represent our equations, so each distinct equations, and the columns, they represent our variables. Okay, so with that said, we're going to take a look at this first equation right here and put it into matrix form. So we have a 3, we're going to call this the x position, y position here, and z position here, and whatever it equals, it will be right here. So we have 3x and negative 1y, and we have 4z equaling to 6. Okay, so that's our first equation here. Our second equation, we'll take a look at this. So we see that we have 0x, we have 1y, and we have 8z, and it's equaling to 0. Okay, and last equation here, we have negative 2x plus 1y and 0z equaling negative 4. So right here, this is our matrix. This is our system of equations that we are trying to solve. Okay? So we're going to do it in the same way that we did last time. So a good first step is to you're going to look in the left corner for a leading one. And if you don't have one in the left corner, you don't have a leading one in the left corner, then you're going to try and make a leading one. Okay, so just let me move this up here. Okay, sorry about that. Okay, so you're going to try and make a leading one if you don't have one. So we see right here that we don't have a leading one, unfortunately, in this corner, but we do see that we have a negative 2 here. So, and 3 minus 2 equals 1. So it gives us exactly what we want. We want to have a leading one. So what we're going to do is we're going to go row 1 plus row 3. Okay? We're going to do row 1 plus row 3. And we see that we end up with 1, 0, 4. And these rows down here do not change. Okay? And the 6 becomes a 2. Okay? Okay, perfect. So now we do have our 1 in there, and we're going to use it to kill everything else in the column. Well, this one is already 0, perfect. This one is not though, so we need to use this 1 to kill the negative 2. Okay? So our next step is going to be, we're going to do row 1, or row 3, plus 2 row 1. Okay? So now we're going to end up with 1, 0, 4 stays the same, and 0, 1, 8, 0, and then 0, 1, 8, 0. Okay, so now we notice that we do have 2 leading ones going diagonally, but we also notice that these 2 rows are exactly the same. So what we're going to do is we're going to cancel the last row. So we're going to go row 3 minus row 2. Okay. So now we end up with 1, 0, 4, 2, 0, 1, 8, and we end up with a row of zeros here. This should look familiar. Look. Oh, sorry. Should look familiar. So we have a row of zeros, so we know we have infinitely many solutions, and when we have infinitely many solutions, that means that we're going to have a parameter. Okay, so we see that yes, we have a leading one in these two rows, and we have a leading one in these 2 columns. But we do have a parameter here. So our z, once again, is our parameter. So let's call it t again. Okay, so we're going to say z equals t here. Now, let's do the same thing that we did in the last problem, and we'll write out what we have. So right now we have 1x, and we have plus 0y, plus 4z equals 2. And we have 0x plus 1y plus 8z equals 0. Okay, so remember we're calling z t. T just means you're choosing any integer, so t element of z. So z, the z with the double line, it means that it's an integer. So if we solve for x, we're going to get x equals negative 4t plus 2. And if we solve for y, we're going to get y equals negative 8t. Okay? So the general form here is, once again, we write it like this: x, y, z equals, and we just basically copy what we have figured out over here. So x equals 2 minus 4t, y equals negative 8t, and z equals t. Okay, where t is an integer. So that's our general solution there.